Hello everyone, and welcome to the workshop on building a clean and simple command line interface in an RTOS environment. Without any further ado, let's jump right into it with today's agenda. We will start off with a brief introduction to highlight the importance of command line interface in embedded software development. We'll then move on to the architectural design of the proposed command line interface. It is clean, simple, and quite different from what you have seen before. I will pause and take a look at the questions that you might have in the chat window and address them right away. Understanding the architecture upfront is essential. Once we have a good grasp of the underlying architecture, its implementation becomes straightforward. After you have seen the design and its implementation, we step back and reflect on what makes a design clean and simple. I'll share my insight along the line of design pattern. The main purpose of my presentation is to enable you to do clean and simple design in your real-world projects. We'll have a live Q&A afterwards, and I look forward to a lively discussion on this CLI design in particular and doing clean and software designs in general. CLI plays a crucial role in interacting with embedded systems. They allow developers and users to communicate with the system through text-based commands, whether it's configuring settings, diagnosing issues, or monitoring system behavior. A well-designed CLI can significantly enhance the usability and the maintainability of an embedded application. Here's a slide from one of last year's presentations, and it captures the essence of a fundamental role that CLI plays in developing embedded applications. To set up the context for our CLI design, we'll first list out the CLI requirements as shown here. It's not intended to be all-inclusive, just highlighting the key ones such as 115 kilo baud rate, text-based commands and responses, including error handling, use of a prompt to enter new commands, etc. It would be really nice to have a command auto-completion and access to command history list. We will see them in action during the implementation walkthrough. Okay, what's the key difference between the CLI design here and the ones you have seen before? The nature of transmitting a command character by character over a serial interface lends itself naturally to a character-based design. The crux of our clean and simple design is to move away from this traditional character-based thinking and treat each console command as an immutable object. The shift from character to object leads to a much cleaner and simpler design. Simply put, the design presented here is not character-based, it's object-oriented. The key word is object. The second part of our design is a standard one, divide and conquer. We will distribute CLI functionalities among a series of functional blocks and watch the movement of a command object from one functional block to its next. In this CLI design, we'll have 3 functional blocks. The first one is a terminal utility program running on your host computer. Our choice is termite, as it meets the requirements of building command objects and supports command line, auto-completion, and history. Its sole functionality is to assemble characters to build a command object. I know this sounds more and more like C++. It's actually indeed the constructor of any command object in the sense that no character will come out of this functional block until the command object is fully assembled. Once again, think about objects, not individual characters. The second functional block is UART, the interrupt service routine for the serial port. Its sole functionality is to assemble command objects from serialized data over the console interface. So it is a deserializer. Once a command object is reassembled, it will notify a console task of the availability of such command object via a semaphore. The third functional block is a console task. It acts as a dispatcher to find and run an appropriate handler function which in turn notifies the task that is designated to process the command by depositing a message in the task mailbox. Here's a block diagram to illustrate both control flow and data flow in terms of how a console command let on is handled as an object. Once a user enters LED space ON and hits the enter key, the command object as shown here is assembled and sent out by termite to your board over a serial interface. The UART will reassemble the command object as shown here and notify the console task using a semaphore. The console task could have forwarded the entire command object directly to the LED task that is responsible for turning on, off, or toggling a LED. After one more task is added to your system to handle a different command, it will become obvious that they all need to look at the verb within the command object and act on it. So we will factor out this common functionality of verb parsing and give it to the console task. Note that parsing does not alter the command object itself. It merely changes its representation from LED space on to standard argc argv format. The console task then finds and calls a handler function, which in turn deposits a message into the mailbox of the LED task. We will come back to this block diagram and sheds a lot of light on how to do clean and simple designs. For the implementation walkthrough, we'll do it in a step-by-step fashion. The first step is to set up LED, UART, free RTOS, and printf. It's like a sanity test to make sure that the demo board we're going to use is functional. The second step is to set up the URISR as a deserializer and add a console task with a simple echo back functionality. After that, we will set up command object parsing in the console task. Finally, we will set up the command handler functionality in the console task and an LED task responsible for turning our LED on, off, or toggling it. Here's our demo setup. We'll have a Windows computer at one end and an STM32 Nucleo board at the other end of a serial interface. ASCII-based commands and responses will fly back and forth between the Windows computer and the STM32 Nucleo board. Now, we have seen how a clean and simple CLI is designed. If we step back and ask ourselves a question, how we do make clean and simple designs in general? There are many aspects we could look at. My insight is along the line of a design pattern. There are two key ingredients. First, a one-way data flow. Once your data are flowing in both ways, it will immediately introduce complexity. Secondly, single responsibility in each individual functional block or C++ class. Any functional block that acts as a kitchen sink for everything will make its implementation convoluted and messy. With this note, we've come to the end of our presentation, and we can start our Q&A part.